given the data, you split it into two parts. Very simple method, okay? Training and testing. But training is training and testing. Testing is not, you don't know what the answers are there. The manager keeps the data with himself or herself, and then he tells, give me the model. I will test it myself, so that you don't contaminate your modeling process with the test data. Test data is your classic testing, okay, of the goodness of your work. The manager says, I don't care what you do, you do whatever you want. You give me a rule, I will test it with my data. Am I making sense? You can do anything you want. You can magically create some function and then give it to him. It's okay with him. He will reward you as long as it is performing well with the test. That is what data mining is all about. Statistical learning is not like that. You systematically go through statistical thinking process and then come up with the best model. So in data mining, what all we have is data, and based on that, you mine the data. Mining the data refers to, first, splitting it into training data and testing data. And this training data further will be split into pure training and validation data. So this becomes three parts actually. Okay, literally speaking, this becomes the simplest method of doing it, 3 parts. Okay, and validate. Okay. So do you understand what I'm saying? You given the data, it's split into 3 parts: training, validation, and testing data. Usually, training is 60%, 20% we keep it aside for validation, 20% for testing. So 100% of data. If I have 10,000 records here, how many I will have for validation? I have total of 10,000 records. How many I will have for validation? 2,000. And for training, 6,000. Testing is 2,000. Okay.
Sir, I cannot see your screen.
Hold on. Okay. So
yes, sir. Thank
you. So given 10,000 data rows, number of rows of data points are 10,000, then I'm saying validation will be 2,000 records are used for validation, 2,000 records are used for testing, 6,000 records are used for training. This is not a hard and fast rule. You can keep here 80% and then 10% and 10%. That's okay. But the idea is you need to give enough for validation and enough for testing. It could be 70% training, and then validation will be 15%. Test will be 15%. I think 70% is also good. 60 to 75%, 60 to 70% is great. You can keep it. Okay. Are you with me, guys?
Yes, sir.
Okay. So this is only one training, one validation data set, and one test data set, right? So what do you mean? Why do you have to do this? You build the model on training. You do all kinds of sophisticated thinking, very advanced thinking. You do whatever you want. Build the model on training, and then you validate it, because this is something is supposed to behave like test. Validation data set will behave like a test, which means you don't have the label here. You have the label here, the outcome here, for which you are building the model, right? But you keep aside the validation labels and apply the training model here and predict the validation label and compare it with the validation label, because that is, you know that. What you don't know is the test data set validation, test data set label. Sounds good? So you keep doing this and iterate, and then you finally got a model. But it is possible you will still work with it, right? But nonetheless, now you say, I have done the best model. You can go to your managers or the competition people and say that, look, this is my best model. They will apply your rules, nothing else. You develop the rules from here, decision rules, the predictive equation from this process. And the manager goes, okay, I will take a look at my data set, test data set. You don't look at me here. Okay, I'll test it out. This is what you talk. And then he does, and then he says, you know what? It doesn't predict very well at all. I get 20% error, and somebody has 15% error. That is what you will give. Nothing else will give. Test data, we may even give the test data, but without label. But the point is, sometimes they won't give you the test data because they don't want the test data to be contaminated in the training process. See, anything you give as information, you can use it, but it can become too specific to that data. You want the model to be generalizable. Generalizable, which means it is applicable very well based on the training model you created, and yet it is not over predicting or under predicting. So that is the challenge of the data mining principle. But then here there is only one sample. The whole data is taken here, training, validation, test. There is only one validation data set and one test data set and one training data set. Somebody came up with the idea, hey, you know what, why don't they, rotate this validation test here, okay? So they said that test is again kept here. We don't rotate the test and test. We don't rotate the, but validation you rotate. So you take suppose 10,000 records are here. This is 7,000 records. This is 15,500 records. This is, let's say, 1,500 records. And then the first sample is constructed like this. This part is a training, this part is validation. Okay. Then another sample, you create another sample for training and validation. So this part, non-overlapping with the previous validation set, this part becomes validation. The remaining this and this becomes the training data set. In the third data set is defined like this. You keep this and this as training, this middle part, middle 20%. Let's call it a middle 20% because there are only 5 variations. Right? So middle 20%. The analyst keeps it as validation data set. So you are training between this and then using this. In the same way, the other two other validation variations are this. The first 20% is, and the last 20% are used for training, and the second 20% is used for validation. Fifth variation of the data is the first 20% is used as validation, is used as training. So you can create 5 different validation data sets out of the original data set given to you. So if I want 5 different validation data sets, cycled over, then this is the best way. So 20%, 20%, 20%. So you have to divide this into 5, 20% because I want 5. If I want 10 validation cycling data sets, then I will have the whole thing will be, this will be 10%. This will be 98%, 80 to 90, 80 to 90%. This is like that it will go. 70 to 80%, 60 to 70%, 50 to 40%, 50 to 60%, and then you have 5 more variations of the validation, cross validation data set. This is called cross validation method. This is the best method you have ever. Okay, and so you build the models here. You build the model here, you build the model here, you build the model here, best model. Okay, for each of these, you build the best model and you take the average model. Am I making sense? Everybody?
Yes, sir.
Very good. Answer?
Yes, sir.
Thank you. So you understand what is mean by cross validation data splits, right? Everybody? Okay. So if I want 20 variations of this, what percentage of validation I will be having? If I want 20 variations. Now I talked about 5, I extended it to 10. If I want 20, you can have 20 variations, cross validation data split. Then what will be the percentage of validation data set? Abhi? Anto?
So can you please repeat?
So what I was saying is, you understand Abhi, you understand what is the validation split mean, right? You understand what is validation split, correct?
Yes, 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 sir.
So when I say I want 5-fold cross validation, this is read this one. Figure 3, but it is 5, 5-fold. This is called 5-fold cross validation. If I want 10, and how much is it? If it is 5, it can happen 5-fold only if these are all 20%, 20%. It's a 20% validation. This one. This is a 20% validation, but it is a different validation. This is a different 20% validation. A different 20% validation, and so on. Right. So then I said I want 10-fold with cross validation. What will be the first one here? This is a 5-fold cross validation, and I can create that, creating 20%, 20%, 20%, 20% like this. 1 second. So I create this. This is another 20%, right? So this is 20%, this is 20%, this is 20%, this is 20%, this is 20%. So 5-fold means I need 5 parts here, which can happen only with 20%. 10-fold means I want 10 parts here, which can happen only if it is 10% validation, right? And I keep rotating that. That is called cross validation. So you have to create these multiple data sets where validation data is repeated, cycled over the different parts of the data set. Okay, so for 20-fold cross validation, usually 5 and 10 is good enough. Okay, I'm just saying it for understanding. If it is 20-fold cross validation, you have to have 5%, 5%, 5%, 5%, because there are 25% chunks you can create. And you rotate this validation. For the first time you build the model, you keep it here or here, doesn't matter. Second time, you keep this part of it as validation. Third time, you keep this part of this as validation. Fourth time, you keep this part of the validation, this part as validation data set, and fifth time, this part as validation. Are you guys understanding what I'm talking?
Yes, sir.
Yes, sir.
So, that's a very important principle. Cross validation is your gold standard. I want to tell you this. Remember that. Okay. If somebody asks you, okay, what will you do? What is the best way of building a model? You just take cross validation, and you know what it is cross validation. Okay. By explaining this. Now, the other important concept is, you have all kinds of complex models you can build. Statisticians, created all kinds of sophisticated mathematics and computational methods for building a best model. But then, as the explosive data come into, as the data came into for corporations, as the data became more and more larger and larger, variety of data and so on, the models are very, very complicated for two reasons. One is technical difficulty, but there is also the number of parameters you have to use to build the model. The more the number of parameters you use to build the model, it is becoming more. So complexity means simply it is a lot of variables. So the question then is, you can keep on adding lots and lots of variables, and you will predict better. But where do you stop? So here is an example. Take a look at this one. Suppose wealth, its relationship to happiness, right? There are only 8 data points up here. Okay. So we are trying to build a model for the relationship between wealth and happiness. And these are the 8 data points. You can do a very simple model, linear model, And there are, these are the errors, correct? These are the errors. Am I correct? And the error is almost 0 here. This is the error. This is the error. Are you with me, Anta?
Yes, sir.
Yes, sir.
How about Hadi? Okay.
Yes, sir.
So,
Yes, sir.
so this is a very simple linear model. That means a line model based on a line.
Sir, they
That
started recording, sir.
I'm sorry.
Recording is started.
Recording is started. It will start. See this one.
Sure, sir.
You see
Just
this
one.
one? Okay. Are you able to see this? I don't know. Are you able to see this? I just want to know. I don't know whether you are able to see. Okay.
No, sir.
Okay. So this is a line. This is a prediction that tells you as wealth increases, happiness increases in general. Okay. That's what this says, isn't it? The data point says that we capture it through a model. You can make it a better model by introducing one more parameter that captures the non-linearity of the equation. So this is called non-linear equation, right? Predictive equation, because it bends. It is not like linear. Linear means straight line. You can see that the error here is less than this one, isn't it? Do you agree with me?
Yes, sir.
And so, Shalini, you can also say, but I want to give them the opportunity to tell me. Okay. So it is a better model because it is very close and the errors are less. You can see lots of points are almost very close to the line. It's a better model. You can do one more thing. You can build a model, each of them with respect to the, a parameter is added for every point. That means you have 8 parameter model. This is the most complex model you can imagine, 8 parameters. This is 3 parameters including the constant. Okay. This is 2 parameters including the constant. 2, 3, 8 parameters. This is the most complex model. More the number of parameters, it's called more complex model. Now, which one we should select? We can select. So what we are saying is that now this is the training data set. The training data set will always decrease, always, because you are trying to perfect for the data that was given to you. It will always decrease. But you apply it for the validation data set because that's all you have. You don't have the test data set, okay? So you have the validation data set. So when you apply it for the validation data set, it will not go down systematically like this. In fact, it will go down, go down, go down, go down, go down, and then it will start increasing after a while because then complexity overtakes. Complexity means more parameters. The variance in the parameter itself overtakes the prediction error compared to the predictive equation. Am I making sense? Kind of intuitive. Okay. The more the number of parameters, it will affect your prediction error. So, you get the extreme levels of very number of parameters like this. Absolutely, prediction error is going to be high because the new data for the new data, this exact modeling will not work. You want to always moderate the modeling with some simplicity. So simplicity is your goal always. Simple model is the best model, but not too simple. This is perhaps too simple. This is simpler, not too simple. This is complex. This is not too complex. It is complex, more complex than this one. Do you understand what I'm saying? Everybody?
Yes, sir.
Sir.
Keep giving input. Thank you. Keep giving input. Okay, immediately when I ask question. So what the prediction error, you kind of if you draw the prediction error for the training, it will always go down, but for the validation set, it will go down, but then it will start increasing. The place where it is increasing is the stop. That's the level of complexity you are allowed. Don't make it more and more complex. Which means what? Don't put more and more new variables, additional parameters into the model. Is everybody good? So you
Yes,
will
sir.
have, this is what is called bias variance trade-off. See, what happens is, initially you have more bias. Okay, that is why initially it is not tallying with this. The bias is this much. But then as you increase more and more, your variance takes over. Okay, and the training error is, variance takes over. The training error is this, and the validation data set, the error is this much. The difference between this is the additional predictive error. So this is the difference between this is the prediction error between the training data set and the validation data set. So what we are saying is that now you look at this validation data set error, as it goes up, you stop there. That's the level of complexity you can deal with. You don't increase further. That means don't put more parameters in the model, more variables in the model, which means more parameters in the model. So this is called bias variance trade-off. The bias part is, initially, bias is there, and then subsequently variance takes over. Okay. So, in terms of explaining it, there's an alternative way to explain it here. Bias variance. This is a great question in the interview. They'll ask you, what is bias variance trade-off? So you simply have to say that is, when you have less number of, when you have too simple a model, it has bias. When you have too complex a model, it has variance. Am I making sense to you? Okay, if it is too simple, that is.
Can you repeat that, sir?
If it is too simple a model, which means fewer parameters, then it has bias. Bias overtakes. But if you put too many variables to make it more and more complex, then variance takes over. So you have to balance it between these two to get the best model. That is called bias variance trade-off. Am I getting you across? So I'm going to show another way of interpreting it. So, let's consider this is the shooting target. Okay, for example, I don't know whether you understand what I'm talking. Shooting target means you keep a target board, and then the training people will shoot at that to say that they are able to hit at the bull's eye. It's called bullseye. I don't know why it's called bullseye. Okay, it's called bullseye. So if you hit this bullseye, you have achieved the target, right? So if somebody is getting like this, what does that mean? There is too much variance in the whole, possibly in the rifle. I'm talking about shooting competition, right? Possibly in the rifle, or possibly in the ability of the individual shooter. Do you agree with me? Okay.
Yes, sir.
Now, so this is called high variance. So it is spread all over. Okay, that's high variance. But this one is not spread at all, and it is on the target. Okay, so it is low variance, and it's also low bias. This is also low bias because it is centered around the target again. It is centered around the bullseye. So low bias, but it has high variance. That means spread all over. What happened was, I actually participated when I was a kid in India. I actually was an NCC student. I actually participated in a competition, shooting competition, because I was selected statewide. And I got this, in the shooting, in my results. I had my own target. I had 10 people were lying down and then taking a shot at this target. I got like this target. What? Immediately my coach came to me, and then he talked to the competition people, saying that, look, there is a problem here. Okay, what he said is that he is hitting in the same place. There is no variance there. He is hitting it correctly, but there is no variance. You can predict that he can do a good job, but there is some problem in the instrument, in the gun, shooting gun. There is some problem. And in fact, he was correct, because I was all the time shooting here, but every time I shoot here, it goes here. Every time I shoot here, and there is no variance here. So you said there is some problem, because we know him. He has been doing well in the training. That's why we brought him to competition. But there's some problem. There is an instrument bias here. Do you understand what I'm saying? The high bias, coming from the instrument. Now, had it happened like this, it didn't happen, it happened. So it's a high bias, no variance. There is no distribution. The points are very close, like low variance. So this is the variance is saying low variance. This is about high variance. This is low bias because it is hitting the target exactly. And high bias because the difference is between the center of this and this is the bias. Center of this and this is the bias. And they found out, and then they, they gave me a new gun and so on. So, but here, again, it's not only bias is there, high bias is there, because it's not hitting here. It is somewhere here, centered here, high bias. But not only that, it also has a high variance, relatively speaking to this one, right? High variance. So what we are saying, you have to, bias variance trade-off means you have to hit it here, and it should not be spread out like this. That is low variance, low bias. That's what you want as the best model for it. So overfitting means, low bias, high variance. Underfitting means high bias and low variance. This is the underfitting situation. This is the best model. This is underfitting. This is overfitting. And here, both bias and variance is overtaking. Okay. Now, what we are saying is that now the model you are looking for is always this one, and that you can achieve by looking at this, how the errors are behaving, prediction errors are behaving as you change the model complexity. As you change the model complexity, your computer algorithm will print the training error and the validation error. They may call it test error. I don't know. The validation error is the likely one, okay? Because you don't want to evaluate test error or error. It should never be touched. Your training model and validating model is within this one, with that remaining data set. What is the data set? This data set. It's whatever the data set that are given to you, that's the only one you can use it for training and learning. So remember this one. You cannot have a too simpler a model. If you can add more variables, add it. If it can predict better. But it cannot be too complex a model. So you have to stop somewhere where you know that as you more and more increase your complexity, you are not going to be any more less, but your validation data set will increase more and more. And you stop here. You say, I cannot build a model beyond this. I should keep it like this. Are you with me, everybody?
Yes, sir.
Yes, sir.
Karanya, are you there? How are you doing?
Yes, sir. I'm doing good, sir. Thank you, sir. How are you, sir?
All right. So,
Hello.
So in real scenario, most of the time we'll get the underfitting, right? So in a practically, if the data sets,
not necessary.
okay.
Yeah, you are audible, sir. Thank you very much.
Okay.
Not necessary. Actually, most of the time we are greedy because we want to do a good job. So we make it more and more complex, which means what? We put all kinds of variables into it. So we try to beat the system. So we try to go near this one. So most of the time we overfit. If you don't have enough variables, enough attributes, of course, you will end up being underfitting. So that is the case of missing variables in the model. So, unobserved variable or missing variable are there, then you will end up having more bias because you didn't achieve enough. You didn't put enough complexity in the model. Are you with me? Understand?
Yes, sir. Yes, sir. Got it, sir.
So you need to know all these things. Now, there are all these notes. I don't want to, you can read it. I have made it for you. You can read it. But what I want to tell you is that let's go back to that. The logistic regression review. This is the scatter plot for logistic regression, right? It is on all the points are on the line. The minus case the negative case or the positive case, right? All the points are there, and you know what is meant by false positive, false negative, true positive, true negative, all those things. No, excuse me, you know that. And I told you, you use confusion matrix to figure out whether the model is good or not, which will help you to calculate different measures like accuracy, recall, F1, and precision also. Okay? So you use all these measurements. Not all the time all the measurements are useful. In fact, accuracy is not the best one. Remember that, especially if the data are imbalanced. If the data, please write it down. If the data are imbalanced, I will tell you what it is. Then accuracy is not a good idea. Get it? Because you know why? You will have maybe you know, out of you will have 10,000 samples, you will have 9,900 samples might be here. Only 100 samples, 9,900 will be negative case, and then only 100 is positive case. And if you do the 9,900 samples, all the negatives correctly predicted, no positives are predicted correctly, then even then you will get accuracy is 99%. Do you understand what I'm saying? Because it is a diagonal, correct items in the diagonal, right? So you get all the 990 here, you get 0 here. So the accuracy is 990 plus 0, which means 9,900 plus 0, 9,900 divided by 10,000, which is 99%. Everybody understands what I'm saying? So even though it is 99%, none of them are true positively. The positive ones are predicted correctly out of 100. It can happen. So when you have, that is called imbalanced data. That means you have more of one case, significantly more of one case compared to the other. That is called imbalanced data. So are you with me on this?
So, yes, sir.
So we want to make sure that we use the right measure, point one. Then we will come back to, okay, given that there are imbalanced cases in real life, how am I going to do the model and how am I going to do the measurements? Will come to that. But what I want to tell you is that accuracy, people, you can use accuracy, but it's not a good idea to rely on that only. Okay, don't rely on that. You need to rely on recall, precision, all those things. So I did explain that to you last time. What is in the recall and precision? Okay, so this is the ROC curve, or it's called the receiver operating curve. It could be an increase in what is in the ROC curve, right? So it is the plotting of this is false positive rate. For every false positive rate, you find out what is the true positive. You can figure that out in the based on the model. Okay, there are softwares that will do that for you. So you have false positive rates here, and then you have true positive here. You plot that, and it will always be like this. Okay, going up like this. Okay, and the highest going up curve is the model related to that is the best model. In this case, the blue curve. Okay? And the red curve is lower than this one, uniformly lower. So blue is the best model. Whatever the model that supports blue curve is the best model. Sometimes it may overlap also like this, go up and down and so on. So the way people use the goodness of measure is what is the area under the curve. That's why area of AU area under the Roc curve is important. It will avoid these difficulties in comparing these kinds of overlapping curve and then going back and forth, up and down. So overall, if you have the area under the curve is bigger than this area under the curve, then you prefer. Do you understand what I'm saying? Why you want to use the area under the curve? Also, many times you don't want to compare the whole curve. You want to compare only based on how much you select. So you select you allow only 20% of the false, 25% of the false positive, for which you achieve the best model from the blue around the 69%, 68% true positive, that is almost 70% true positive. So you are going to use only target only this much of the data, this much of the data only. That is where 25% of the false positive cases are to be handled. So, you have to work with 28% of the false positive cases. You can never get zero false positive percentage, because if you get zero false positive percentage, you get zero true positive. Understand? And basically, you are saying you don't have enough samples. So my point is, you have to maximize the. You are going to maximize always. Take the best model is one that is uniformly higher than all the other curves, other model curves. Point one, and the second one is even if it is not there uniformly higher, you know that you want to control the false positive, but because false positive, your goal is to achieve maximum true positive, but for any level of true positive achievement, there is some amount of false positive. You have to face it. You have no choice. So you say, well, okay, I'm going to work with 10% of the false positive cases, or 20%, or 30%, or 40%, 23%, 35%, and so on. So you are saying I'm willing to allow that much false positive in my cases. Okay, then what is the true positive? So in this case, in this example, this is 28%. This 28% achieves 70%, true positive cases. Understand, everybody? So that is how to interpret. Is everybody good, clear with this? Yes. Anto and Abhi?
Yes, sir.
Very, very important, both of you. Remember this, because in the end, it comes down to working with this curve. This is called the receiver operating curve. So having done all these things, now I also mentioned about how to use profit function to select the best cut point where you will stop selecting for targeting purposes. So here you were thinking differently. That is, you're saying I will not allow more than 20%. I don't want to allow more than 20%. What is my true positive? That is what. But then sometimes you may say, I am not willing to take any negative profit for my target. So if you say that way, then you are working with profit function. That means when you create a decile report, this is also called a decile report. Please note it down what is meant by decile. Okay? This is called a decile report. This is another way of selecting. So for every top 10% of the sample, top 10% of the highly scored probability, okay, there are 900 true positives and 100 false positives. Okay, so you took 10% of the 10,000 is, because we have 10,000 samples here. Okay, sample is 10,000. 10% of 10,000 is 1,000, right? So what we are saying is that we have 2,000 observations or positive cases. By 10%, you are able to achieve 900 out of the 2,000. Okay, 900 out of the 2,000 positives you are able to achieve, identify, and then 100 of the false positives came into your selection. Okay, because it is 2,000 samples, you are able to achieve 45% recall. This is also called recall. So you can recall, how much you achieved, and then cumulative false percentages out of 8,000, 100 is not 1%. But the profit is 34,000, because every correctly identified creates value of $40. Every incorrectly identified creates a loss of minus $20. So if you calculate that, 900 of them are correctly identified. 900 times 40, which is 36,000, minus 20 times 100, 2,000. So that's why it is $34,000 profit you get. If you just stop with this targeting alone, you get 36,000. If you go to the next 20%, next 10%, then you get cumulatively you have 1,200 true positives, and then 800 false positives. Okay, So likewise, you calculate the the profit here. 1,200 times 40, that is 48,000, minus 800 times 20, which is 16,000. Am I correct? Everybody, 48,000 minus 16,000,
Yes, sir.
you get 32,000. So as you increase more and more, because more and more false positives are accumulating. That's why this curve is like this, right? This Roc curve. It's another type of Roc curve. Okay, it's not true false positive. Um, because we are talking about you can say this is we are talking about here, we are talking about within each decile how much false positives are captured and the true positives are captured. So it's an interesting way of combining the decile and the true positive and false positive rates to get this curve. Okay, so you can continue to do this, but when you come to this one, you are going to, that's the last time you are going to get more and more, you are more and more taking the losses from the false positive. So it will decrease, but you won't go beyond this. You might think that now, why do you have to even go here? I want to stop here, 32,000 there, I want to stop, or 34,000, this is better than this, this is much better than this, right? You may say that, but then for business purposes, you may want to reach more and more people, because eventually, I will have more people in my target list with whom I can communicate and convert them over time. So you may stop here, or here, or here, or here, or even up to this, but then it becomes negative afterwards. So usually you don't want to go beyond, this one. Even here, you don't want to come here. Okay, maybe you will end up stopping here, 30% or 20%. Okay? So this is the profit-based decile, using decile report, profit-based curve. So this is called profit-based curve. So now with that, I want to go back to the Titanic decision tree logistic function, and then you'll see another example. Okay, that's our purpose. You can take 5 minutes break or 10 minutes break. Okay, 10 minutes break, and then we'll start again. Oh, we cannot go beyond another half an hour, right? So is that okay? I will continue. Let me finish it. Okay.
Yes, sir.
It's okay for me.
Abhi has to go. Abhi has to go.
Yes, sir.
Okay, so let's do this. I have given the data set for you, so I'm going to run it again one more time. So this is the place where you downloaded the data. So I can run this, both of these, and then okay. So how about I run the whole block of thing? Okay, whole block. So this one, run the current chunk. So I didn't have any problem. I was able to access a data set, training data set, and testing data set. So this is the famous story of Titanic. Okay. Even if you don't know, I sent a PowerPoint deck. So read the PowerPoint deck, the story, or lots of details about the variables and so on. Okay. Is everybody good with this? Did you have a chance to look at it, Anto and Abhi? Because we did last week.
Yes, sir.
Okay. Let's continue. So these are the variables. I read the training data set. I was looking for structure in the test data set. So what is the difference between training data set and test data set? Test data set. Okay. So the training data, the data frame for the test is for structured train. That is what the first one is. So it has 891 observations. Train data set has 891. So and then you go down below, then you get test data set that has 418 observations. The number of variables are different. Here it is 12 variables, training, there is 11 variables. One of the variables is missing in testing. Can you find out what it is, everybody? You can look at it and something is missing. something is missing in the test data set. I want to know who is going to give me the answer quickly. What is that variable that is missing in the test data set? That is training has 12, test data set has 11. What is the variable that is missing?
Survived.
Survive.
It is
Excellent.
missing.
Survive. Survived is missing. Okay. That is your target variable. That is the outcome variable you are going to predict. And in the test data set, you are not supposed to have the set, right? Because that's how you can validate, your model is good or not. So remember, he is not following cross-validation method in this, the whole RMD file or markdown file. I'm not using the I'm not using validation word. I'm not using cross-validation. I'm just using build the model on training and validate it using the test data set. Okay, so you won't have outcome variable in that test data set. That is my point. Because you don't need it. You are going to use this test data set to see whether the model you are building the training data set fits in there or not. So you won't know it. As a manager will know it, so that he can compare. Oh, you predicted this much. The real values are real records are like this. Who survived, who did not survive. I compare these two things, and then I will make a decision whether the work you did is good or not. Am I making sense? So that's why test data set doesn't have. But in order, we can't just solve the problem without the labels for this. So we go and get some labels from the in the Kaggle competition. Somebody submitted with a high score, we took their labels so that we can compare with them. Does it make sense to you? That is the plan.
Yes, sir.
Okay. Thank you.
Yes, sir.
Anto? Super. So we want to do a little bit of quality and data quality analysis. So we want to know how many of the variables are missing, which variable is missing, how many times, and then we do look at it using the visualization and so on, and then we impute for important variables. We impute the missing. Okay. So let's run this quickly. So what does it say? This is age variable. So this is the easiest way of remember this command, very useful. And so Saranya, Gaushali, and Abhi. You want to know
Yes, sir.
for each of the variables how many missing values are there. It's very simple command. Even if you have 10,000 attribute columns in the data frame, it will just quickly give you. It says the cabin has 687. There is something called cabin variable. Okay, see, it is not available in the test area. But here, cabin has some information, some of them are missing. Okay? So that cabin area misses for a lot of people. What is the next most missing variable? That is age. Age is missing. 177 people, age is missing. Embarkation, from which place they boarded the ship. Two places, two records are missing. Okay, so it gives you an idea, right? And then let's continue through this. Test, also we want to do in the test there is pad one is missing, cabin is missing to 347. This is for training. Okay. So and then we want to code because survived, it's a qualitative variable. You cannot use the qualitative variable to model. Okay, you have to use 0 or 1. So we are transforming the survived variable into 1 when that column is called survived, right? But its values are also survived or not. Okay, so we are going to put we are going to convert survived as 1 or 0. Okay, so we combine for the test data set. We take all of them to be survived. That's the problem. But anyway, we are just taking all of them to be survived. Okay, and so we merge both the data sets so that we can compute imputed value, age value, for example. That's why we do all these things. So we do that. Let me just combine that, and then wherever I have class variable that is nominal variable, I will make it as factor because that's how R runs the analytics. You have to call them as factor. Okay, otherwise it will consider as some kind of a string variable. It's not a string variable, it's a factor variable. Okay, so we do for passenger ID. We want to put the factor. We don't need it, but you can put it factor. I don't need it because we are not going to use passenger ID in the model, isn't it? We will never use that. So survived is a factor, and then CC class is a factor. Okay, so those are the two variables we want to use it as factor. Now we can see which is factor, which is numerical, which is yeah. Columns. So now we want to check how many are missing. Age is 263 now. Cabin is increased. Okay. Number of possible missing values because we combine the test and data refers to combination of test and train. Okay. Data refers to combination of test and train. So and then now we do some visualization to figure out whether visually we can understand that or not. The media package, the library is not there. I don't know why. So it says that here. So I'm going to just click. Nowadays we get information. So okay, it's done. Now I call to the library and then mismap, okay, for the data. It requires use mismap data, something or oh, it is there. See, it is the RMD file. That means you are not looking at the view here, right? It's only when you run script file you will have a view here where you can see the map here. But because the RMD file, it will come below. Okay, remember that. Huh? So that's what these are wherever it's white color. That means almost saying the cabin is the worst case scenario. Next is age. So now. Now what age, we can probably take an average age from all the data and post it. Okay, that's a very common thing people do. It's not the best thing to do, but let's just do it. Okay, so I take the mean whenever it is available. Whenever data is available, I take the mean of the age from the data frame, which includes both the training and testing, and post it wherever it is missing for the age. That's what this means. Do you understand what I'm saying? And taking the
Yes,
mean
sir,
of
understood.
the age. Thank you, madam. Thank you. Anto? Okay. All right.
Yes,
so,
sir, we did it on that day.
Oh, we did it on the day. Okay, so let's just move on quickly. So let's just do that. Then we can see how good the model is. Okay. I think we did the model also. Right?
Yes, sir.
So we did some transformations like this. Look here. Whenever it is missing for the fare, we take the average, right? Now average for the fare again. That's what we do. And then now we check. Then none of them will be missing. What is going on? Southern is way higher than other places of boarding. So because I let's replace the two missing values in involved by S. Okay. So it is. Sometimes you can use maximum likelihood method to replace impute the value or average method. If it is a continuous variable, use average method. if it is a qualitative variable, you find out which is the most likely class, and you can attribute that. Southampton has a lot more data for this. So we are doing that. So for 2 people, watermelon is missing. We just replace them with S4. Now nothing is missing. And then here, now we split back to training and testing. Okay, we combined it to do this, the imputation, missing value imputation one. Now I am running it, then I'm saying, you remember I made it as 1 survive, right? In the test case, I want to make it null because that is just done for some calculation, intermediate calculation purposes. So here is the GG plot of it comes here below here. There you go. So it says aesthetics is the x-axis is gender and the y-axis is the count. Okay, the count by the category called ggplot aesthetics. There's a trap PC class, the first class, second class person. That's what this one is, number 1, 2, 3. So we are looking, you can see that now there are almost 90% of the 90% of the people in the first class are women, right? Women, and then the males are mixed. Okay, that's very interesting, isn't it? Okay, so this is for the second class also highly populated, but a lot of people in the third class. Maybe these are all a lot of people are I don't know, servers are there. Perhaps that's a part of the issue. I don't know. So let me interpret it correctly. The people who are in the first class, okay, and if you are a female, you are more likely to survive. That's what this means. Okay? If you are a third class and if you are female, then you are likely to survive 50-50, almost 50. But in the first and second class, females are 100% likely to survive. And you can see the third class males almost because there is too many of them, right? There is a lot of people. There are a lot of males are there in the third class. Okay? So what we are saying is, people who survive among the males is also high in the third class because there are too many of them. That's all. So let's do some additional. Now I'm going to split the train into train and combined data. Train $survive. Split ratio is 80% and 20%. So split data. Subtrain is 80% of the data you have, and sub 10. It's not the test data set, but if you created a validation, you can call this as a validation data set. That is a better word. Agreed? Anto and Abhi?
Yes, sir.
Yes, sir.
So, so now I have, imputed, I have selected the training and testing, validation, better word as validation, that's it. And I am going to build a model. There's something called R path. This is what the decision tree is, okay? Just one decision tree. So R part refers to decision tree. Let's run that one. Create a person. It just split that. Good click. So it's taking time, but it will take. All right. So it is created. Yeah, it's created. But I don't know why. Maybe I can connect. Okay. It's only accumulating the code. Okay, that's fine. So let me go back to I want to close. This is yesterday. Yeah, this is the one right now. So I have set up the data now. I split the data. Now I'm doing the decision tree. Okay, so let's do that. R part. That's called R part. Okay. All right. We just took the model. That's fine. The model is here. The model is there. This is what the model is. Now I do the I do want to find the predicted values out of the decision tree and then compare it, right? The confusion matrix. I want to create that one. This is how the decision tree is looking like. Okay, that's the most important thing is gender, age greater than 13 or less than 13, and then the PG plus T. That is the decision tree. Then we want to calculate the confusion matrix. You see, it is doing the prediction equation. Prediction. Yeah. There is a data same value prediction. Okay. So I'm supposed to have seen that data set, right? The prediction is. So I can just play with that and see. And so this is what the predicted values are. Are you with me? So this is the index, and the fourth index row in that data set. That is new data is subtest. You remember subtest is the one we split from the joint data. Okay. So fourth record is 1, 21st record is 0. It is split on the misorder, right? It's not the order. So don't be surprised. Okay. 21, 20, 24, 28, 29. 29 is predicted as survived. 4 is predicted as survived. The between 4 of them are predicted to be not survived. Okay. Now I want to do the cross tabulation. You can see that for the test data set, 41 are actually 42 plus 26 are the actual target case survived, which is 68. Okay. So actual class 1 is predicted 42 divided by 68. 0 class is predicted out of 110, 100 of them are predicted correctly. Okay. So that's what this is. So let's do this. And it says accuracy is 79%. Okay, let's do this one. This is working. Wow. Okay. So I got the confusion matrix here. Is this one? You see, accuracy is 70%. 90% confidence interval around accuracy is 35% to 93%. Sensitivity is same as true positive, 66%. Specificity is 1 minus false positive. So you are 1 minus false positive is specificity. Please write it down. Okay. And specificity is 75%. And from that, you can calculate the false positive rate, which is 25%. Do you agree with me? I said specificity is 1 minus false positive. Yeah,
Yes,
so
sir.
false positive. Thank you. Thank you, Abhi. Okay. And whenever it is target, the positive predicted value means whenever it is target, 80% of them are correctly identified. Whenever it is reference, which is the case which are not survived, 60% of them are correctly identified. That's what this predictive positive value is, and then predictive negative value, or positive predictive value, negative predictive value. There is something called balance accuracy. So, this is what balance accuracy is now. Balancing the sample, because this this accuracy may be a small one, possibly because you are predicting the reference class, not the target class, more accurately. Okay, so there is a balance. When you balance it, it comes down to be 70%. Okay, because if you remember, the accuracy is 70% here, and here also balance accuracy is also very close to 20% if you use the balance. So you have to think about all these things, when you are doing your confusion matrices. Okay? Now let's continue to finish this one. Go and finish this one. You have to do this. You have to call this. You have to do this confusion matrix. There is a function called confusion matrix under library caret, and that prints a lot of these many things to do. Okay, let's continue to finish this one. Let's go continue to finish this one. Okay, so that is what the Titanic model is all about. Okay, so for the Titanic model, we have done all these things. We will do this again one more time. Certain other things we might do to compare and so on. So let me see whether I have it here. None. So in the next class, what I want to talk to you is generalized linear model, which means your dependent variable could be Poisson outcome variable, a rare event. Okay? Poisson model is useful for rare events, and it is also a counter. It's not continuous variable; it's a counting variable. 2 people are there, 3 people are there, 4 people are there, or number of people who died out of COVID after giving the vaccine. So which is a rare event. It's not a massive event, rare. Okay. So we will do those things in the next class. Is there any question? Is there anything that I can spend more time? This is how this is the example for R. Okay. Any other question I can answer for you? Now, I want to show you an example of a multinomial model. Okay? That means multiple classes are there. See, this is the survived or not, but sometimes there could be multiple classes. Okay? So, how do we do that? That is called multinomial model. So, I want to use this, Princeton. I want to use the Princeton example, multinomial logistic example. So let me go there. This link is there in your PowerPoint deck. So this is binary classifier. Did you vote in the last election, for example? Okay, 0 means no, 1 means yes, and there are only 2 classes. For example, alternatively, did you use Public transportation, do you prefer public transportation or drive a car? So prefer to drive in 0, prefer public transportation means 1. If outcome or dependent variable has more than 2 cases, then we call it as a multinomial case. Okay, so let's do one problem. So here, for example, do you agree or disagree with the prisoner? Disagree, neutral, agree. What is your socioeconomic status? Low, middle, high. What do you like to do in the weekend? Rest, go to movies, and school. So if you have data set like that, how do we model? That's called this multinomial model. Okay. In the next class, I will do the multinomial modeling and also Poisson method as examples of generalized linear model. Okay. I want to close the session today this time. Any questions? Comment here. Any question on
No, from
Abhi
my
and
side.
no? I'm sorry.
No questions, sir.
Super. Okay, Anto.
None, sir. But this decision tree RMD file, it's not in the drive, I think.
I will send it. Send it to you or directly or through document. Okay.
Okay,
Yeah,
sir. Thank
I
you, sir.
probably have multiple versions of this. You know, this one I didn't give you, last time I gave you different one. Okay, I will send it to you. This is this one, okay. Not this one. This one I did. I'll send it to you.
Okay, sir. Thank you, sir.
Thank you. Thank you very much. No, so my instructions will be over by next class. Monday, it will be over. Okay? Then we will go through more sit and work with the last person, Supriya. So Supriya will be with you on class. She will go through these examples again and bring some similar examples. That's what she will do. Okay. There are a lot of examples we have in regression as well as logistic regression. I'm talking normal regression as well as logistic. We'll go through those examples and hopefully you'll enjoy them. Okay? Because these are very practical cases that you can go and use it in your job. Thank you very much, everybody. Have a great rest of the evening. Is it good?
Thank you, sir. Good day to you.
Thank you, sir. Thank you, sir.
Have a good day. Thank you, Abhi.
Thank you,
Thanks,
sir.
Saranya.
Thank you.
Thanks, Bhaskar.
Thank you, sir. Thank you, sir. Thank you so much.